Hello students, good day all. Today we are going to learn in this session chapter 13, the kinetic theory of gases. In this introduction, molecular nature of matter, behavior of gases and the kinetic theory of ideal equation. One by one we can see, children. Yes students. See, Boyle discovered that the law which is named after him in 1661. Boyle, Newton and several others which are tried to explain the behavior of gases by considering that the gases are made up of tiny atomic particles. See, the kinetic theory which was developed in the 19th century by Maxwell and Boltzmann and others, it has been a remarkable success. After that, Richard Feynman, the greatest, one of the greatest physicists, he was there in the 20th century, that he considered that the discovery of the matter is made up of atoms, that he has taken in a very significant way. And Feynman that would like the atomic hypothesis. The atomic hypothesis, which we can say that the communicated to the next generation of creatures in the universe. The atomic hypothesis that we can say all things are made up of atom and little particle that moves around in perpetual motion. And it is attracting each other when they are in a little like a distance apart, but it is repelling upon being squeezing into one another. Let us see in detail through the kinetic theory of an ideal gas. Yes students, Boyle's law, the statement that says that at a constant temperature, volume of a given mass of a gas which is inversely proportional to the pressure. Then mathematically we can relate that V is inversely proportional to 1 by P. So that we can say that PC that is which is equal to, that is PV which is equal to constant. Right. So V which is inversely proportional to the pressure. So volume which is inversely proportional to pressure. Right. Now the graph which we can say that relating P, that pressure versus volume, that it will be, if suppose you have taken in the x-axis that volume and here the pressure. You can get the graph, the nature of the graph in this way, then the temperature which is equal to constant versus P, that is pressure, versus volume, that is 1 by V. If we have taken 1 by V, then the nature of the graph will be straight line. It will be directly proportional. The temperature which is equal to constant. So here you have taken that volume in the x-axis and the pressure which is in y-axis. Got it children? So Boyle's law, the statement says that if the pressure remains constant, then the volume of the given mass of a gas which increases or it may be decreases by 1 by 273.15 of its volume, that is at 0 degree Celsius. For each 1 degree Celsius, it may be rise or fall of temperature. Mathematically, we can relate this to that Vt which is equal to V0 1 plus T by 273.15, or that is equal to V0 273.15 plus small t whole divided by 273. Here we can write that Vt by capital T, which is equal to V naught by T naught. This, it comes from that 273, that is 273.15 plus T, which is equal to, we can say that capital T, that is temperature, and 273.15, which is equal to, we can take it as this T naught. By this way, we have related this Vt by T, which is equal to V naught by T naught. From this relation, we can write that V by T, which is equal to constant. Right. So by relating this as the graphical representation, by taking the temperature here in the x-axis, that is in the constant way, and here we have taken the volume, it will be, we will get the straight line. That means the pressure is constant. Right? So the next one is Gaylussac law. The statement says that if the volume which remains constant, the volume is constant, then the pressure of a given mass of a gas which increases or decreases by 1 by 273.5, 15 of its pressure at 0 degree Celsius for each 1 degree Celsius which rise or fall of temperature. This statement we can relate through the mathematically, that pressure, the temperature which is called P naught into 1 plus T by 273.15. So that is equal to P naught 273.15 plus T whole divided by 273.15. Right. That as we can write Pt by P naught, which is equal to T by T naught, or we can write P by T, that is equal to constant. Right? This we can draw for this, the graphical representation. Yes. In x-axis you can take temperature in Kelvin, and here in y-axis you can take pressure. So you will get that straight line and the volume, that is equal to constant. Right, children? Yes. Ideal gas. See, if suppose the gas which is ideal, a gas which obeys the ideal gas equation, that is PV which is equal to nRT, at all the temperatures and the pressure, we can call that it is a perfect gas or it is an ideal gas. See, what are the characteristics for an ideal gas? The first point we can say, the size. The size of the gas molecule, that is negligibly very small. Then we can consider it as an ideal gas. And there is no force of attraction that among the molecule of the gases. So, what the deviation which is there from the ideal gas behavior? That we can say there is no real gas actually is truly an ideal. It has the 3 different temperature. We can show through the graphical representation now that PV by NT, which is equal to the pressure. Here the PV by NT, which is equal to R. The value is 8.314 joule mole per Kelvin. That means joule mole power minus 1 per Kelvin. Now, the PV by NT, which is called the pressure, different values by relate through the graph. Now, in the x-axis, we have taken the pressure in that ATM as a unit and the PV by NT. That was the value we said that 8.314, that is joule per mole per Kelvin. Right. Now the ideal gas equations which we can say, which is here in that straight. What are the three different, that is maybe like the temperature 1 which we can consider here, the temperature 2 which is for the pressure, how the pressure in the PV by NT, it is varying, it will be moved through this way T2, and the gas equation which is for another temperature, it may be like this. So we will get the three different temperatures for PV by NT which is equal to the pressure. Pressure versus the PV by NT. For this is the deviation from the ideal gas behavior. Yes. Now this is the comparison between the experimental PV curves versus the theoretical curve. We have taken the PV curve with how Boyle Is Law it is getting varied. A little bit the variation will be there, of course. The ideal gas equation, because of there is no gas, truly it will be like a curve, right? We'll see that through the graphical representation, right? Now you have taken that for the PV curve. So pressure versus the volume we have taken. Now it may be you have taken this as the temperature 1. This is I have taken for the temperature 1. If suppose I have taken this as this line as the ideal gas, right? So or else we can take this line as the real gas. Then how with the Boyle Is Law, it is little bit getting varied from the real gas. So this maybe will come for the ideal gas equation. And like temperature T2 I have taken in this way for the real, and for it's getting varied from the real gas. That is only you are going to know through this graphical representation. And also we will do for the TV, that is temperature versus the volume. If suppose the temperature you have taken that in the y-axis and the volume you have taken in the x-axis, the real for the pressure, it may be in this way, the V1, and for P2, but how the Boyle Is Law, it's getting varied for the ideal equation. The dotted line you can take it and consider for the ideal equation, children, right? So this way it is getting varied. We are comparing the experimental and the theoretical curves for the PV and the TV, right? So this is for PV curve and this one is for the temperature volume curve. Yes, the pressure which is exerted by a gas. According to kinetic theory, the molecules of the gas which are in a state of the continuous random motion, they collide with one another actually, and which is also with the walls of the vessel. So whenever it is getting collide, what will happen? The returns with the change in momentum of an equal momentum will be transferred to the wall, so that it will be conserved in nature, or we can say it's a conservation of momentum. And as per the Newton's second law of motion, the rate of change of transfer in the momentum which is equal to the force which is exerted on the wall. That means what? If suppose a large number of molecules which collide with the wall, a steady force which is exerted on the wall. So the force which is exerted per unit area of the wall is the pressure of the gas. So the gas which is exerted or exerts the pressure which is due to the continuous collides of its molecule with the walls of the vessel. Right? Yes, students, so far we have learnt about the molecular nature of matter and the behavior of gases, the kinetic theory of the ideal gas. So we have learnt elaborately, students. Thank you.